Today we're going to talk about truss analysis using what we call the method of joints. So again, first, before we get into working through a problem, I'm just going to lay out the step-by-step procedure that we'll use to solve these problems, and then we'll start with a really simple truss. So the thing about method of joints is the procedure is the same no matter how large the truss is. So we'll look at a really small truss, but if you can do a really small truss, you can do a really large truss. It's basically the more truss members we have, the longer it will take to work through the problem. But the procedure, again, is going to be exactly the same either way. So, as a reminder, the reason or the times that we use method of joints really coincide with the times when we want to solve for all of the member forces, right? So our procedure, okay, it may sound a little bit complicated or intimidating at first, but once we work a couple of problems, it's going to make perfect sense. And I think you'll find that the process itself is not very complicated. So the first thing that we do is we want to look at a free body diagram of the entire truss. Okay, so essentially when we look at method of joints, or method of sections for that matter, we're looking at the truss in two different ways. The first way that we'll look at it is as a whole structure, right? So if we have a truss, let's say again, just a simple truss, it's simply supported. We want to look at a free body diagram of the whole truss. So in this particular truss configuration, we'd have 4 joints, 1, 2, 3, 4, 5 members. So when we look at a free body diagram of our entire truss, okay, we want to find the support reactions. Okay, we want to find the support reactions, and to do that, we'll include externally applied forces, so we could have F1, F2, F3 here. Again, those forces are going to be always applied at the joints on a truss, but we want to include externally applied forces and solve for the unknown support reactions. Okay, so in this case, we're going to have an X and a Y support reaction at A, and a Y support reaction at C. Okay, so our first big step is looking at the truss in its entirety, looking at those applied forces and using those to determine the support reactions. Okay, so once we have the support reactions, that's when we get into the true method of joints procedure. So our second big step is to take a free body diagram of each joint. Okay, so again, the joints are the places where 2 member forces are connected. We said that we're basically idealizing those joints as single frictionless pins. And so when we take a free body diagram of that joint, we're looking at the joint and looking at the forces that are coming into that joint, including the support reactions. Okay, so to do this, we're going to isolate a joint with no more than 2 unknowns. Okay, so at this point, we will know the support reaction. So we want to isolate a joint with no more than 2 unknown member forces. Okay, so let's look at that. So if we had a truss, again, just a simple truss, and let's say we had a Y reaction here, call this point A, AY, and AX. Okay, as long as there are no forces applied at this point, then our unknown member forces would be here. And this member and this member. So this would be 2 unknown member forces. So we could start by isolating joint A. Okay, and if we isolate joint A here, this is still B, this is still D. Then our unknowns are AB and AD. If we isolate that joint, joint A, okay, essentially, we're looking at equilibrium of a particle, okay? So we isolate joint A here. We're going to have AY and AX, and then our unknowns here will be AB and AD. Okay. Some more notes about this is basically when we isolate this joint, we want to draw the free body diagram. Okay, which is what we've done here. Again, this sort of represents equilibrium of a particle. So we have an object here. We've got forces acting on the object. All of those forces are concurrent. And so the reason we can't have more than 2 unknowns is because all these forces are concurrent. So we can't take moments about anything, right? Because they're all intersecting. So if we take moments, the moments will go to 0. So we can only look at a joint with 2 or fewer unknowns at a time. Okay. When we draw our unknown member forces, okay, we want to draw them in compression. Okay, so we're going to assume unknown member forces are in tension. Okay, when we say that we're going to assume they're in tension, that means we draw them with the arrow away from the joint. Okay, so we're assuming here for now that member AB is in tension and member AD is in tension. And the way that we show that is essentially showing the joint itself in tension. So we're showing that this is creating a pull, if you will, on the joint. So when we assume that all the forces are in tension, okay, rather than trying to guess every time, that can get kind of messy. We're just going to always assume that it's in tension if we don't know it. And then so any answer we get, positive answer, will indicate that it is tension. And any negative we get will indicate compression. Okay, so this is a little bit different than the process that we use when we look at the overall free body diagram and we try to guess whether AY and AX and so forth are in tension or compression. When we're looking at individual joints of a truss and working through the truss, if we try to guess the direction, it gets to be really difficult to sort of keep up with our signs and whether things really are in tension or compression. So this procedure really simplifies that a lot. After we have completed the first joint, okay, the next step is just to work our way through the entire truss, looking at each joint, okay? So we're going to move to the next joint. Okay, with 2 or fewer, less than or equal to 2 unknowns. Okay, and then repeat step 2. Okay. We want to keep doing this until the truss is completely solved. Okay, unless you're just specifically asked, for example, what is the forces in AD and AB here, right? If we're looking to solve for the entire truss, we just want to keep doing this process until we've solved for each of the member forces. And the last thing that we'll do is we're going to draw what we call the force summation diagram. All right, so we're going to show that. That's basically a free body diagram that shows the forces in it. Okay, so once we've solved all those forces, we can summarize them in what we call a force summation diagram. So we'll do an example of that here in just a minute. Okay, any questions about the general process here for solving trusses? All right, so like most things in structures, I think the best way to really learn it and then understand the whole procedure is just to work through as many examples as we can. So we're going to start today with, again, a simple truss and work our way up to more, basically larger trusses here. So call this example 1, method of joints. All right, so we're going to have kind of that same configuration here. Call this A, B, C, D. have a pin at A and a roller at C. We're going to have a 2 kilonewton force applied horizontally at B and a 2 kilonewton force applied vertically downward at D. This segment is 9 meters long and we have 12 meters here. Right, so for now, I'm just going to use this sketch as our free body diagram and as our force summation diagram so that we're not having to recopy this thing several times. So I just want to first show, right, our support reactions, because step one is to take a free body diagram of the entire truss. Okay, and then solve for those support reactions. Okay, so here we'll have AY. Okay, again, when we take the entire truss or a beam and we're looking for the support reactions, I like to try to guess the direction for those support reactions because it's usually pretty obvious. Like here, we have one X force to the right. That means that our X force at the support will be to the left. So I'm going to go ahead and guess that that's going to be to the left. We have one reaction here at C. Show that one going up, CY. Okay, so those are our 3 unknown support reactions. Okay, so let's call this step 1, just so we can keep in line with the steps that we laid out earlier. All right, so sum of the forces in the X direction equals 0. We have negative AX plus 2 kilonewtons equals 0. So we've got the support reaction here. We've got one applied here. So here AX is equal to 2 kilonewtons. It's positive, so we drew it correctly to the left. So I'll just note that here. Next, we can take moments. Again, I'll take moments about point A here, since that's where our pin is located. So first we have the 2 kilonewton force here times our vertical distance of 9 meters. Okay, that's going to be clockwise, so that's negative. Next, we have our 2 kilonewton force here at D times our horizontal distance here, 12 meters. That's also going to be clockwise, so that's a negative term. And then last, we have CY times our horizontal distance here, 12 plus 12, gives us 24 meters. That's going to be counterclockwise, so this term will be positive. All this equals 0. Okay, so we solve for CY. We get CY is equal to 1.75 kilonewtons. Okay, we get a positive there. So we guessed that direction correctly as well. So it is indeed up. Then we have our sum of the forces in the Y equals 0 to solve for AY. All right, so we have AY positive minus 2 kilonewtons, D plus CY, all equals 0. And we can plug in our 1.75 kilonewtons for CY. And that gives us AY is 0.25 kilonewtons. And we get positive there as well, so AY reaction is up. Okay, so the first step of truss analysis is what you already really know how to do, right? Taking a free body diagram of the entire structure, basically laying out the unknown support reactions with all the applied forces and making sure to include everything, and then applying our 3 equations of equilibrium to solve for those unknowns. Okay, step 2 is where we want to start looking at individual joints of the truss and drawing free body diagrams of those. Now, one of the questions that I always get asked a lot seems is where to start. And so there's no magic place to start on a truss. So basically it has to have either 1 or 2 unknowns. It can't have any more than 2 unknowns or we can't solve it. So the answer is really that you can start anywhere that fits that criteria, but I typically will just try to start at the left if I can. So we can usually start at the left end of the truss as long as there are no applied forces at that joint, right? Because the way that most trusses are laid out, usually there's only 2 members that connect at that left-hand joint. That's not always the case, but that is the case here. So here we have 2 known forces at A, the X and Y support reaction, and we have 2 unknowns, AB and AD. So I'm going to start at joint A. Now, if we were to look at joint C, we have 1 applied force and we have 2 unknown forces. So we could start at joint C as well. It just makes more sense to me to work from left to right if I can. So that's why I'm choosing to start at joint A here. So we want to draw a free body diagram of this joint, show AX and AY, and then we'll show the unknowns here. So this is step 2. Okay, step 2, we're going to isolate joint A. So the free body diagram will start with just a point representing that joint. And we have AX and AY, which we solve for here. AX is 2 kilonewtons to the left, AY 0.25 kilonewtons up. So we're going to draw those on there. 0.25 for AY and 2 to the left for AX. Okay, so it's important to make sure that we get those directions correct here for the things that we know. Okay, next we want to draw our unknown member forces. So here we have AB and AD. And again, we want to draw those in tension. Okay, so always draw them in tension if they're unknown. So here we have AB at an angle here. We'll draw that in tension. And we have AD horizontal. We'll draw that in tension. Okay, and we're going to need the slope of AB. Okay, so looking at this truss, we have 9 meters vertically, 12 meters horizontally. So we have 9 and 12. We can simplify that slope. Okay, those are the actual dimensions. So we can simplify this to get our slope in a more familiar format. So if we divide both of these terms by 3, that gives us 3 vertical, 4 horizontal. And we know that that's 5 for the hypotenuse. So 3, 4, 5. So we're just going to translate that here to AB. So we had 3 vertical, 4 horizontal, and 5 for the hypotenuse. Okay, so the important things to remember about this step and all the steps that will come when we are looking at an individual joint is, first, we want to be sure to draw everything that we know in the correct direction. So in this case, we know the AY term, we know the AX term, and we know what direction those are actually in. So we want to show those accurately in their correct directions. And then anything that's unknown, we want to assume its intention. So we'll show those going with arrows away from the joint. Okay, at this point, we just want to apply our 2 equations of equilibrium. Okay, so we don't have 3 equations to use since it's a free body of a particle. So let's apply our 2 equations of equilibrium. There we go. So our 2 equations of equilibrium, sum of the forces in the X equals 0. Sum of the forces in the Y equals 0. Again, we can't take moments because everything intersects at a common point, so there's nothing to take moments about. With these problems, we can apply these in any order, just like when we're looking at free bodies of an overall truss or free bodies of a beam. Okay, but again, I like to think about it just a little bit to make it as easy as possible. So in this case, if we were to start with summing the forces in the X, we have AD, we have 2 kilonewtons, and we have the X component of AB. So we have 2 unknowns in the X direction, okay? But if we were to take forces in the Y, we have the known force here and the Y component of AB. So if we start with taking forces in the Y, in this case, we'll get an answer and we won't end up with an equation. So again, if you start with the X, there's nothing wrong with that. You'll just end up with an equation and you'll have to go back and substitute something in there. So let's start with summing the forces in the Y here. Set that equal to 0. So again, we have the Y component of AB. Okay, so 3 over 5. Okay, Y component of slope over hypotenuse of slope, 3 over 5 times AB. That's our Y component of AB. Plus our reaction here, 0.25 kilonewtons. Okay, and there's nothing else in the Y direction, right? We have the Y component of this term. We have our Y support reaction, and that's all. So we set this equal to 0, and we solve for AB. We get AB equals negative 0.42 kilonewtons, okay? And again, getting a negative here just means that this member is actually in compression and not in tension like we drew it. So this is a negative, and I'll mark down that it's in compression. So I want to mark this answer as I'm working through. Now we'll take sum of the forces in the X direction equals 0. We have a positive AD we have the X component of AB. So plus, again, we're writing our equation to match our free body diagram. So AD is positive on our free body diagram. The X component of AB is positive, and that's going to be 4 over 5. So X of slope over hypotenuse of slope times AB minus our 2 kilonewtons here at X. Okay, and that all equals 0. All right, so we've got our support reaction at X, X component of AB, and AD. We've solved for AB, so here we can substitute in. All right, this is another thing that I think sometimes can be confusing. The best thing to do is just not overthink it too much here. But again, we're writing our equation based on our drawing, right? So we're putting negatives or positives into this equation based on the way that our free body diagram is drawn. And so we're not going to change anything when we solved for one of the terms. So we solved for AB. We know it's in compression, but we're still using our free body diagram, which shows that intention. So when we substitute here, we're going to substitute in either negative or positive. We got a negative here since it was compression. So negative 0.42 kilonewtons. We'll substitute in for AB. Okay, and so that will take care of whether AD is positive or negative, right? So again, we want to draw our free body diagram with everything in tension. When we solve for X and Y here, we'll get negatives or positives, but we're going to write our equations based on our free body. Okay, so once we solve for AD here, substitute in AB, we get a positive 2.33 kilonewtons. Okay, since AD is positive, that means it's in tension. Okay, any questions about step 2? All right, let's go back here to our free body diagram for the entire truss, right? So once we find these terms, these members, what we're doing in order to create our force summation diagram is we're basically just showing those on our free body diagram. Okay, so for example, we got AB 0.42 kilonewtons in compression. Okay, so compression, opposite of tension, means that the arrows go toward the joints. So to show that this member is in compression, we want to show it with the arrows here going towards AB, A and B. And the value we got for that was 0.42 kilonewtons. Okay, so I like to show the arrows, and I also like to write here that is compression. Okay, for AD, we got 2.33 kilonewtons in tension. So since this member is in tension, we'll show it with arrows going away from the joints. And we can sketch that value in here, 2.33 kilonewtons, and tension. Okay, so when we create the force summation diagram, essentially what we're doing is we're just drawing tension and compression and putting the values in for each of the members. One of the reasons I like to do this as I go instead of waiting to the end is this is a sequential process. Okay, so we started at joint A, but now we have to pick another joint to move to complete the truss. Okay, so we can look at this until we can move up to B here. At B, we have one applied force. We have our known force, AB. We have the unknown here, BD. And we have unknown here, BC. So we can move to joint B, and there's two unknowns. Let's look at joint D. We can move to joint D here. We have one BD unknown, BC is unknown. Everything else is known. So we could also move to joint D. Okay, so again, it's basically just a choice, one or the other. You could flip a coin, or you could try to look at what might be easier. So if I'm looking here, we've got BC at an angle. We have AB at an angle. But at D, everything is applied vertically and horizontally. So D is going to be a little bit simpler to solve. So I'm going to move to joint D rather than joint B. Okay, so this would be step 3. Move into that next joint. So here we can move to joint B, two unknowns. Or joint D, two unknowns. Okay, but D is simpler to solve. Okay, so I'm going to choose D. So I had a question about the arrows. Okay, so arrows going away from joints indicate tension. Arrows going toward the joints indicate compression. Okay, so basically when we look at the free body diagram of joint A like we did, we showed that A was in tension. When we solved AB, we found that it was in compression, so that arrow was actually going toward the joint at A. And we said that these members are continuous. Okay, so member AB is continuous between A and B. So if it's in compression anywhere, it's in compression everywhere. So we have to show arrows going toward each of those joints.
Do you put the reaction forces in the final diagram?
It's up to you. You can, but really the member force is the most important thing, because the support reactions, we need those, but they're a lot easier to include when we draw a free body. So mainly there are a couple reasons to show the force summation diagram. One is using it like we are now. It's going to help us to make sure that we include everything when we draw the next free body diagram. And it's also going to help us kind of do a check to see, does it seem reasonable? So in this case, what we have so far, we can say that, yeah, it seems reasonable. Because if you remember when we talked about the way that trusses sort of behave like beams, and that beams bend, so there's a lot of tension on the bottom, there's compression on the top of the beam. And the same is true for a truss. So here we have tension on the bottom, compression on the top. So it seems like we're at least on the right track with our tension and compression here. So that's a good question. All right, so again, we can move to joint B or joint D. I'm simply choosing joint D because everything here is vertical and horizontal, and the math will be a little bit easier here. So let's draw free body diagram of joint D. Okay, so this free body diagram, again, starts with just a point representing the joint here, D. Okay, now, again, everything that we know, we want to draw in the direction that we know it is. Okay, so in this case, we know that AD is in tension. So here we'll draw it in tension. 2.33 kilonewtons. We know that the force that's applied at joint D is applied downward. So we'll draw that straight down, 2 kilonewtons. And everything that we don't know, we're going to draw in tension. So here we have dB vertically in tension. So vertically up, we have DC, okay, which we'll draw to the right to show tension in this case. And those are the only 4 forces we have to intersect at joint D. Okay, so we have no slopes to deal with, which is nice. So we can just apply our equations of equilibrium here. Sum of the forces in the X equals 0. We have DC. It's drawn positive. DC is drawn negative since it's to the left, so minus 2.33 kilonewtons equals 0. So DC is 2.33 kilonewtons positive. So DC is in tension. dB, we take some forces in the Y to get dB. So dB is drawn up, so it's positive. Minus 2 kilonewtons applied here equals 0. So dB is equal to 2 kilonewtons positive. So dB is also in tension. Now we can go back to our force summation diagram here. And we want to put DC on there, show DC in tension. So arrows going away from the joints there for tension. And that was 2.33 kilonewtons. Excuse me, dB was 2 kilonewtons. Tension. DC, arrows going away from the joint for tension. That was 2.33 kilonewtons tension. Okay, any questions about this step? Okay, so now basically we have just one force that's unknown. So our only unknown left here is member BC. BC. Okay, so if we think about how to solve for BC, there's 2 different ways we could do it. We could move to joint C. We have 1, 2 knowns at joint C. 1 unknown. Okay, move up to joint B. We've got 1, 2, 3 knowns and 1 unknown. So would it make more sense to choose joint C or joint B in this case? We have 4 forces at B. 2 of them are at a slope, 3 forces at C, and only one of those is at a slope. So it'd be simpler to go to joint C. Again, it wouldn't be wrong to go to joint B. It just might take a little bit longer and a little bit more work. All right. So let's take a minute and let you guys attempt to solve here using a free body diagram of joint C to solve for member BC.